So, good morning, good afternoon, good evening, depends on where you are in the world. So, we are here today to see the talk by Professor Himanshu Thapliyal from University of Tennessee, USA. And before giving the floor to him to talk about energy and cybersecurity constraints in cyber physical system, a very hot topic nowadays, I will do some brief announcements. So if you lost some stocks that were done since 2020, you have more than 150 talks available in this YouTube channel, so for free. So and then if you don't see in the YouTube the talk you want, you just do a search, and you are going to find all these talks. So. I also would like to invite all you to prepare your papers for LASCAS 2025. As you know, this is the flagship conference of IEEE Sequencing System Society that is being organized in a location in Latin America each year. So as international conference of CASS. And best papers are invited to submit a version to TCAS 2. The one selected to TCAS 2 appears in the months of the conference. And during the conference, there is a additional evaluation of the presentations, and then some papers are invited for a full extended version to TCAS 1, special issue about Lascas. And so it's a great opportunity to come here to south of Brazil, where we are. So Bento Gonçalves is very easy to reach. It's the main, more traditional wine region in Brazil, close to Porto Alegre. So you can fly. You will be able to fly to the Porto Alegre airport very easily. Then 2026, Lascas will be in Arequipa, in Peru. And 2027, it will be in Panama City. Also, as you should know, IEEE Secret System Society is also sponsor of another important conference that is being organized since '83, SBCCI. So this year it will be in João Pessoa. The papers were already selected, but you are still able to prepare your papers for the 2025 edition that will be in Manaus. So the gateway to the jungle. So it will be a new edition of Chip in the Jungle. Last time that it was organized there was in year 2000. So we are going to be back 25 years later. So you still have several months to prepare your papers too. And as you know, CAS is doing 75 years this year. And to celebrate this, for the ones that were never member of CAS, there is a free CAS registration for professionals and students. This is available till next August. So, and the IEEE student membership is about $14 nowadays. So please, if you are not yet a member of CAS, it's a great opportunity to join. But we are here today to attend the talk by Professor Himanshu. So Professor Himanshu is currently an associate professor at the University of Tennessee, Knoxville, USA. He received a PhD degree in computer science and engineering from the University of South Florida, Tampa in 2011, where he received the Distinguished Graduate Achievement Award. He has been ranked in the top 3 among scientists throughout the world in the field of computer hardware and architecture for the calendar of year 2022. He is the recipient of 2019 NSF Career Award and 2020 IEEE Computer Society TC VLSI Mid-Career Research Achievement Award and 2022 IEEE Computer Society Distinguished Contributor Award. So a large set of awards. No? Congratulations. No? He has also authored over 200 journal conference articles, with over more than 6,750 citations, 3 US patents, and received the Best Paper Poster Award at IEEE Internet of Things, Cyber and Information Security Research Conference, and IEEE Computer Society Annual Symposium VLSI. He's serving as General Chair of the 2024 IEEE Computer Society Annual Symposium on ISVLSI, and that will be organized in about 10 days, no, in Knoxville, and the 2023 ACM Great Lakes Symposium on VLSI. So thank you very much for your talk.
Okay, thank you, Professor Ricardo Rees. You can hear me, right? Well,
Yes, it's okay.
okay. Okay, thank you, and thank you everyone for coming. It is very nice to be here, and I'm really thankful to Professor Ricardo for inviting me to give this talk. And as Professor Ricardo mentioned, that we will be hosting ISVLSI from July 1 to 3, 2024 here in Knoxville, Tennessee, USA. And with that, I like to welcome you all to come visit us in Knoxville and attend this ISVLSI symposium this year. So today I will be giving this talk on energy and cyber security constraint in cyber physical systems. So let me start. You can say this gives us a perspective of cyber physical system, which consists of a combination of sensors, actuator, processing units, and communication. You can say they communicate via network. And usually these cyber physical systems, you can say, has application in medical devices, smart homes, cities, environment monitoring, and industrial processes. And nowadays a lot of critical infrastructure like smart grid, you can say smart transportation, these are pretty good, really, you can say operational example of the CPS. And this is one such example that has been shown here is an is a, you can say, is an automotive thing, and it consists of a lot of electronic control units which are talking to each other. And nowadays in the future people are talking also about the vehicle to vehicle communication and all those things. So you can say these are all really very good examples of the cyber physical systems. Now, this is one example. If you see in the cyber physical system, this Internet of Things really plays a big role nowadays. And you can say the applications, here is one such slide that shows how this IoT is being tied to smart cities and villages. So if you see nowadays, let's say in US and in many uh, other other countries in the world, people are trying to, you can say, make the cities more smarter in nature. And also some of the rural areas people are working on to make them advanced and smart. So in that way you can see that you have the smart healthcare, smart farming, smart home, and if you're in the village it could be a smart hut. People are also trying to make the education as pretty smart, because you can say during the COVID time there was a lot of things were done at remotely. So maybe it is possible that not all places you have access to, you can say, good schools, and you can say, because some places may be slightly remote, then how can you still provide the quality of educations to those places remotely? So that could be a very good example of a smart education system. Then you have smart energy, smart governance, and of course you can say many times in this world there are some issues with crimes and all those things. So surveillance and security can also be very important. And then you can say there are so many other critical infrastructure like transportation and all those things. So now, if you see, this is one example of this IoT computing thing. You can say they have application in communication. We discussed already, and over a period of, you can say, last few years, you can say there are significant growth in the Internet of Things devices. For example, if I look around when I was a graduate student around 2011, 2012. There were things, but not too many if you see connected from the internet perspective. But nowadays, even let's say we take an example of your home, or you have a lot of smart bulbs, you can say smart cameras, you can say you have smart fridges, smart TVs. So everything is becoming more and more smart, and you can say the IoT has become the key component of our life. So now let's move forward. And then what is the issue? The issue is that there are a lot of security vulnerabilities in these smart computing devices. And this is one such example of the cyber attacks that has happened, you can say, on a particular period of time. And this data is, you can say, you can look into this year data and you can find some information. This is just a representative information. Then you can say that critical manufacturing, energy, communications, and these are, you can say, are the major places where the cyber attacks has happened. You could have seen that people are also attacking the hospitals with the ransomware attacks and all those things. So you can say the cyber attacks are everywhere. And if you see, interestingly, these IoT devices almost form 33% of these total cyber attacks. So you can say, if you look into many of these IoT devices that you purchase, they do the job, but the question comes is that are they really secure? And during the COVID times, this attack has also been very significant. And you can say the attack on CPS, the cyber physical system, estimated to reach by 50 billion USD. So it's a significant amount of organization. And you can say 80% of the healthcare organization reported the compromise of their data. So you can see that nowadays you are seeing a lot of news and all those things that, oh, this is being hacked, this medical record has been released and all those things. So this is really, you can say, important challenging time from the security. So now, if you see over a period of time, the rise of attack vectors from over the small computing nodes, it is expected that you have 14.9 billion smart computing devices by 2025. And this compromised node could be in the water distribution, it could be the electric grid, it could be the gas pipeline, healthcare sectors. So whatever the critical infrastructure which is needed for our day-to-day activities and also for our security, you can say, can be exposed, right? And this is one example that is being shown here, that people can put the remote attack via internet by using some sort of a buffer overflow attack. This is some example, or you can put some sort of a this say cache timing or the row hammer type of attacks. You should have heard about this Spectre meltdown and all those things that people have exposed the vulnerabilities. Now here also people can do some sort of local attacks in your hardware when people have access to the devices. One such example could be a smart meter and smart card or smart meter. People can, you can say, look into the smart meter. They can put some, you can say, side channel analysis on this one, get the keys out, and then it might be possible that they are never paying the electricity bill. So this is some examples that could be, and if it is your credit card and all those things, then people can do some other transactions also. So you can say it is a really interesting scenario from the security aspect. And this is another interesting aspect, you can say, that shows about the security vulnerabilities in the sensor based devices. And when we talk about the sensor based devices, you can say the cameras, the consumer electronic and energy devices. So one interesting thing that I will show to you in the today's talk, that we know that many of these Internet of Things devices has already sensors being deployed. Now, interesting thing is that can we use the sensors not as only as a mechanism to provide the sensing features, but also as a mechanism to provide security. So in other words, that is, can we develop some security primitives that can help us to improve cybersecurity with the help of sensors? That I will also show in today's lectures. So if you see the challenges, if you see many times in many of the systems, is that especially when you talk about Internet of Things, they are pretty small devices, the battery operated, they are sometimes deployed in remote locations also. So sometimes you have a issue that how to develop a system which is energy efficient, and how to make sure that you're also providing security, because as soon as you add some extra things there, then it is going to consume some more power and your battery is going to drain so quickly. So now it's an interesting challenge that, how can you develop some system which is secure and which is also energy efficient in nature. So let me take an example to you. So let's say you have a wireless implantable device in your body, and now interestingly, that is wirelessly implantable, so wirelessly charged. So that is then it can be wirelessly charged. That is good, but it can also now offer some security vulnerabilities there. Let's say if you have battery operated devices inside your body, and of course if you put a lot of security features there, let's say, then the battery is going to drain so quickly. So do you really want to get operated so soon every time to replace the battery? Maybe not, right? You want that battery is there and you want the battery to last for a long time. So how will you develop some solution which are secure, but also you can say energy efficient in nature? So these two things are, if you see, are orthogonal to each other. So that's why it is a challenging problem. And today in this lecture, I'm also going to show you that how we have tried to address some of the solutions, that you develop solutions which are secure, but which are also energy efficient in nature. So this is some example of the side channel attacks that is performed at the hardware level. So this hardware level, you can say people can perform some side channel analysis. Side channel analysis means that people can, whenever a computation is happening, some signature is also being leaked, and this is more like a side channel from which people can find that what is going on in the system. So people can put some timing analysis based attacks. People can also put some power analysis based attacks, some electromagnetic based attack. This is side channel, and people can do other types of attack also, like the fault analysis, where people can intentionally injecting the faults and all those things. People can do some probing attacks, but here, or people can do the reverse engineering also. Reverse engineering is, these are all different types of attacks, but today here we'll mostly talking about the side channel analysis attack. And some example that I'm going to talk to you is targeted towards this power analysis based attacks, and these attacks could be applied in different types of encryption algorithms. So this is one such example. So this is an example of a side channel based differential and correlation power analysis based attack. So here you can see that that you have a system, in this case a particular smart card, and people want to get what is the keys and all those things that is being used for, you can say, encryption and all those purposes. So here you have the input data on the left hand side, and this is an actual device. So you do that and you measure some power consumption through that. Then you create a hypothetical model, you can say, and this model can be Hamming weight or Hamming distance based off some model. You create a model, then you correlate them, and from that you identify that what is the correlation between them. And whenever you see there is a high correlation, you know that that is the possible key that is the system is used for encryption purposes, and then you have already hacked the device, at least from the keys perspective. So that is the vulnerabilities, and these types of attack has been used. This is one example where people have, you can say, this is a smart bulb deployed in the people's home, and so people tried. So hacker have in this case put some sort of a correlation based power analysis attack. They were able to identify the key, what key was being used in this particular smart bulb, and from that they were able to access the whole smart home environment. So in other words, just by hacking the smart bulb, they were able to get access to the smart home environment. And this work has been presented some time back in one of the conferences by the people. And now this is one such example. So in other words, we may think that it's not going to impact, but people can really perform this type of attacks in the real world. Another interesting scenario in this case, that let's say if you travel, you can say in a metro or all those things, then people, you have this card which you can load for reloading the purposes. So that let's say you are traveling, then that card money is over, you want to reload it so that you can use it again. So here people have done some correlation power analysis based attacks, and here without actually paying for the for that fare, people were able to recharge their financial card. So that is pretty interesting. In this case, this can be revenue loss for the, you can say, for the government or whatever the companies that are using this type of systems. This is another example where a key was stolen from the financial card. So people, like, you can see that these types of attacks are for real, and it is possible to perform these types of attacks in the real world scenarios. So now when these attacks are there, you want to develop some solutions to make them secure. And especially this slide shows the this DPA countermeasures that people have explored at different levels. For example, at the algorithmic levels, you can develop some solutions such that let's say when you are writing the hardware code for that particular algorithm or something like that, you design the algorithm such that people cannot identify what is going on, because the algorithm is designed such that the power is always uniform in nature. So it is very difficult for people. Then people can also look into the circuit level solutions. And here in this particular talk, I'm going to talk about the circuit level solutions. And in the circuit level solutions, we will talk about especially the customized, you can say, approach, where people can do the full custom designs type of solutions. So that the benefit in this particular case is that if you're looking for the algorithmic solutions, then that algorithm solution has to be customized for different algorithms. But in this case, particular cells, because we are looking into full custom design, then once you develop some sort of standard cells or something like that, then these standard cells can be used for different types of encryption algorithms. They can be even deployed for, you can say, your lightweight cryptographic algorithms, which can run in IoT devices. It can be also been used for, you can say, your post quantum types of algorithms. So in other words, the applicability of the customized solutions in this particular case or developing standard cells could be very wide, because the same cells that you have developed one time, you can use it for different encryption algorithm. For example, let's say you develop a secure XOR gate, which will show some example. Then secure XOR gate can be deployed in different algorithms. So that's the sole idea. In the right hand side, you will see some parameters, and this is from one of the papers. So you see in this case, interestingly, whenever you try to make some solution, you can say at least circuit level, energy efficient and all those things, with you will have some security features coming up. But interestingly, you can say there will be some power overhead, or so one interesting thing in this case, of course, this means, let's say my system is consuming X amount of energy right now, and then I provide to make it secure, then the energy of the system is going to be X plus Y, where Y can be some number between whatever, it could be 5%, 10%, 30%, whatever. So in other words, whenever I'm adding security, this Y factor is going to play a role, because it is going to increase the energy consumption of my system. So what we are looking into this case is, rather than I'm adding this Y factor, can I reduce from this X the original energy that is being dissipated and reduce it further? So here we are going below X rather than X plus Y, and the solution that we are looking in this case is a mechanism called adiabatic computing or energy recovery logic. This is one study that has shown that even after fabricating the chips, the adiabatic logic or this can be at least 30% more energy efficient than the CMOS counterpart, and also be resilient against the differential power analysis based attacks. So this is the sole idea of this adiabatic logic. Here, if you see, whenever you design a normal CMOS based circuit, you have a constant VDD that is given to you. But in this particular case, these type of systems are driven by the clock, and these clocks can be in the form of a sinusoidal clock or a trapezoidal clock. So consider this is more like, in this particular case, this is a clock, and this is my function f and f bar, and this is my energy recovery circuit. This means it is helping me to recover the energy rather than dissipating all the energy. So that's the sole idea. Okay. So here, if you see, this is a pretty good example of the seesaw. So let's consider, let's say this is a clock, and instead of the constant VDD, now you have the clock driving the system, and the clock goes up, and it takes some amount of time called T for the clock to go from 0 to VDD. So here, if you see, the clock goes with some amount of time. So at that time, you can say this seesaw is represented like this. So this means the energy, let's say, is going from here to here. So this means the energy is being supplied from the clock to your output nodes, and your system is computing now. Now, after some time, you can say that once you compute it, you can say, because the clock is going to fall down, and that is being represented in this particular case here. You can say that in this particular case, the clock has, you can say, started falling down. So the clock has started falling down, but the output nodes are now at a higher potential. The clock is at lower potential. The energy is going to retransmit back to the clock source. Now your clock source should be smarter in nature, that it should be able to recycle the energy. So that is one interesting aspect. So that's why these type of circuits has to have a clock generator which is not which is dissipative in which ideally will dissipative in nature, but it's not fully dissipative, is able to recover some energy actually. So that's the sole idea. The more you develop a system which is less dissipative in nature, this clock generator, this means you will develop better system. Another efficient thing that you can think in this particular case is, so whenever your system is transiting from 0 to VDD, this means at that instant of time, this system can be modeled by a resistor followed by a capacitance that is charging the node. So at that type of system, you can say there will be some energy being dissipated through the path. And the CMOS, you can say whenever in the CMOS particular type of devices, you have almost like 1 by 2 CVD square of the energy being dissipated on the resistive path. But in this type of adiabatic system, because it takes some, it's a clock based system, so it takes your some time, let's say in this particular amount of time called t, to go from 0 to VDD. So that's why you can say this t, the transition time, in this case the energy is given by RC by t c VDD square. In other words, in this particular system, in this case, if I make my t, this transition time, bigger and bigger, then I'm going to have less energy dissipation, right? If I make this t is greater than equal to 2RC, where R is the resistive path and C is the node, this capacity load at the output, then I will have the less energy dissipation than the standard CMOS. If I make t goes to infinity, this means I make the system very, very slower in nature, then my E dissipation in this particular case is almost equal to 0, which is, we can say, of course. So what we are trying to understand from t greater than infinity, what we are trying to show to you in this particular case, that if you make your system using these adiabatic clocks and run it at a very slow frequency, like a low frequency in megahertz or kilohertz range, then you can develop really energy efficient system. Of course, when you're running the system at the gigahertz and higher range, then it's not going to always give you good results, because the t has become shorter now. But if you're looking for IoT based systems or some sort of medical devices where you really want to, where you don't care about that much high frequency, you're happy with the low frequencies, megahertz or kilohertz range, then this is cool idea, because now you should be able to recover some energy, and you will be able to have less dissipation than the standard CMOS. So now we talked about the energy perspective. Now let's see how this system becomes secure. So this is a standard example of a CMOS inverter, and this is an equivalent design of another, you can say, another type of logic family that is still based on CMOS. You can say it is, but it is dual rail in nature. So what is, why you want to make it dual rail? Because you want to make it dual rail because instead of time you're computing f, you're also computing f bar. So because of dual rail nature, the system automatically hides some signature from the observer, right? Because now the system is computing f along with f bar, so the power signature looks almost uniform. So in this particular case, it's a CMOS, right? This is a CMOS inverter. You can say in this case, when the system is transiting from 0 to 1, 1 to 1, 1 to 0, 0 to 0, you can say this there is a non-uniform power dissipation. So for an attacker, they can look into this power profile and understand what type of transition is happening in the system. If you make a dual rail based type of system, just using some sort of logic style, the conventional logic style, then you see that in this case, it has become secure now because the power profile has become almost uniform, but the current has become much more higher. So in this case, it is 69 microampere. In this case, it's 142 microampere. So what will happen because of the conventional approaches? Your system is going to become secure, but now it is going to consume much more energy and much more power in the system. So your system is secure, but it may not be good for IoT type of applications. Now let's take an example. If you use the adiabatic logic in this class, in this particular thing, which I'm going to discuss more in detail now, you see in this particular case, the system is consuming uniform power, and also the peak current is significantly reduced. Since the peak current is reduced and the system has become much more uniform in this particular examples, the system is going to be energy efficient and also be secure against these differential power analysis based attacks, because the system is always consuming a uniform power dissipation. So that's one motivation. We looked into that. So now this is interesting example I showed that once these things are there, of course, if you have the normal system, because of the energy consumption, you can say your battery is going to drain out. if you use some of these adiabatic logics, then your battery is going to last for slightly longer time. And then you can use these systems in wearables, smart health, smart home, or any type of application, cyber physical type of application, which are not operating at very high frequencies. So this is one such example. So this is one example of a logic gate that is designed from one of these adiabatic logic families that is proposed by one of my research group, actually. So here you can say, as I told you, this is the instead of constant VDD, you have the V clock. So this is the V clock I was talking to you. It going from, it's a trapezoidal clock, it's a 4-phase clocking scheme. And and again, it's a dual rail logic. So you compute, you can say whenever you're computing, you compute XOR along with XNOR. And it also, whenever you have the input, you have the A along with this complement. So you provide inputs along with this complement, and the output you get your this output F along with this complement F bar. And you have the V clock here. So the interesting thing you can think, in this particular case, the power consumption is almost uniform. So that is pretty interesting. So because now, by using the idea of adiabatic logic, we are able to recover the energy. And since the power consumption has become much more uniform, so it is difficult for attacker to attack the circuit, at least from the power analysis based attacks. So this is some example. So what we did in this particular case, we took some technology, and as I told you, by using this adiabatic logic, we are able to recover the dynamic energy. But of course, since it is a dual rail now, so there will be more transistors there, so it might be possible that they may leak more. So interesting aspect could be, can I use some sort of technologies such as FinFET, tunnel FET type of technologies, or some other emerging technologies, which can also help us to save the leakage power, right? So now you can use adiabatic logic to save the dynamic energy, and these new types of emerging devices, uh, or FinFET is already being used, but some type of new emerging devices which is uh, coming in the future to also reduce the leakage power. So if we just did some study, and this is the conventional CMOS, and this is the, you can say, adiabatic logic, which is implemented in, you can say, the CMOS based transistors. If you implement this adiabatic logic into the FinFET, then we are calling it FinCell. If you implement this adiabatic logic into tunnel FET, then we are calling it tunnel FET. So you can see that, interestingly, with the use of emerging devices, you can further have increased, you can say, saving in terms of energy. And of course, the security is also will be much better. So that's what I want to tell you, is that merging adiabatic with emerging devices could be very interesting scope for doing the research, because it can help you in both ways. So this is the attack. Now we performed some attack on one of the lightweight encryption algorithms, and it's called present 80. So here what we did is that we implemented the same present 80 using the CMOS gates, and then we implemented this with this adiabatic logic styles. In this type of things, you can say, with the CMOS, when we perform this CPA or DPA, different types of attacks, the key has been very much came out very quickly in CMOS. But in adiabatic logic, the key is, you can say, this is the key, but it is key is somewhere hidden. And even after, you can say, that many traces, it is difficult for attacker to get the key out. So that's the sole idea. So in other words, we are able to save the energy, but we also make it secure now. Now moving back, interesting thing, as I discussed with you, we talk about that these systems are dual rail in nature, because so it is computing F and F bar, and you have sense amplifier on the top. So what is the problem now? The problem is that these systems are taking, because of dual rail property, taking 2x, the almost the 2x area overhead. It is 2x plus some number area overhead compared to the normal CMOS based approach, right? So the number of transistors is almost 2 times. So now we looked into that, can we deploy and develop some mechanisms so that these adiabatic logic styles can be implemented into uh, using a single rail instead of dual rail. So this is one such approach that has been proposed in the existing literature, not for security. It was been used for designing some logic gates. Then my student, he started looking into this problem, and he said, can we implement some security primitives from that one? So if you see this logic style, it's almost like a CMOS, because you have this function F, and this is the clocking network. This is almost like how you implement a CMOS based design with a PMOS on the pull-up side and the NMOS on the pull-up down side, and you just put some clocking network on the top. And I will show to you in this particular example the transistor overhead is almost only 2 transistors more than the CMOS. So now if you see this one, by using this idea, we are able to develop some adiabatic logic style which are single rail instead of dual rail, and the area overhead in this case is only this clocking network on the top. And if you ask me, usually this clocking network on the top and on the bottom is hardly 1 or 2 transistors, so it is, the area overhead is not that high. So now we try to implement this idea. This is a single rail, and you can say by single rail ideas we are able to save some good amount of energy compared to the dual rail based method, and also compared to the CMOS based methods. And we showed that the system is secure against attacks. Okay. So now very interesting aspects, we looked into security. Now still I feel that we can do more here. So because why we can do more here, because in the end it is, there are some more transistors here, we are saving energies and all those things, but the transistor count is 2x. Then our objective is, can we reduce the transistor count, right? Because it is good, it is able to recover energy, but there is overhead in terms of transistors. How can we do that? So one interesting aspect that we started looking into, one of my students has looked into in his master thesis at the time, is, now if you see, you have the adiabatic logic, and we already showed that it is secure. Security goes up. Its power is less, so power is this means it is low power in nature. But the issue still is that there is area penalty. Area is slightly bigger. Then another interesting thing we looked into, what about if we merge two different computing paradigms together? One is called the approximate computing. In approximate computing, you think in this case you are not computing the exact result, because in many applications such as image processing and all those things, you don't need an exact result, right? For example, let's say you're watching a TV, you're watching a 4K pixel TV or a 2K pixel TV, or something like you can say a lower pixel TV. So for the human eyes, it's not always possible to differentiate between these things. So we can, in many places, you may not need an exact computation. You are fine with approximate version of that one, right? So in this particular scenario, what we thought, actually, of course, in this approximate computing, the security is an issue, but it is low power. It has low power because you are computing the approximate result and the exact result. The area is less. Can we merge these two together? So we merge, you can say, adiabatic logic along with approximate logic, and we propose a solution called adiabatic logic based approximate computing. And we feel that this type of application could be very much useful for edge devices. So if you see, if you are making some, you can say, intelligent edge devices, you can say, that can do some sort of machine learning task or intelligent task, then adiabatic logic can be combined with some of these approximate computing ideas, and it can give you some sort of an edge computing device which is secure. Power is also, you can say, low power in nature, and also the area is substantially reduced. So this is one example I showed to you. This is the CMOS based adders, and if you put a simple approximate adder using CMOS, this is the number. If you merge adiabatic with approximate computing, then you can say that the number is significantly reduced, for example, from 12.73 to 0.539. So significant amount of energy reduction you can get. And one interesting aspect I want to show to you is that, let's say you have CMOS based adder, then the number of transistors, let's say 28, right? 28 for a 1-bit full adder. Then if you made an approximate adder, then it gives some number to you reduction. But we were able to show that by using this adiabatic and approximate adder computing together, you can develop a very, very reduced area design, which is also energy efficient. And you can look into some of the papers that we have published actually in this domain. So now a very good, interesting aspect I showed to you. Now let's move on from the cryptographic aspect to the hardware security primitive. And one interesting aspect of the hardware security primitive is called the physically unclonable function. So here in the physically unclonable function, the interesting aspect is that you, because of the manufacturing on the process variations, no two devices can behave the same. For example, if you look into our DNA, which each one of us have a unique DNA, and so that makes us unique, right? People can know that this is Himanshu, or this is Professor Rees, or this can be another person, right? So people can identify us from our DNA. Similarly, these chips are designed, and because the manufacturing process variations, there's a good probability that one chip will behave the slightly different way from the other chip. So can we capture these features and develop some security primitive from that one? So this is the idea behind the idea called physically unclonable function. So you put a challenge, the same challenge to chip 1 and the same challenge to chip 2, and you get a response 1 and a response 2. And if the response 1 is not same as response 2, then you have a puff circuit there. Actually, that's what we want to look into. So in that case, people can identify this is chip 1 and this is chip 2, and it can solve a lot of security vulnerabilities problems. And so people have looked into developing these puffs by using silicon based methods. You can look into some examples of the arbiter based puff, or similarly from the silicon based puffs, people develop this convert these SRAM cells, and this SRAM cells can be used for developing some of these puffs, because the reason is that whenever you have SRAM cells in your system, as soon as the system boots up, you don't know that which state these cells are going to initialize. Some of them can be initialized in a 0 state, some of them can be initialized in 1 state, some of them can be in unknown X state. So this can be unique signatures, which you can create this unique signature for this particular chip if it has an SRAM within that. So people have used this idea for developing silicon puffs. But we also, what we looked into that is, as I will show to you in the next few slides, how can you use sensors and energy harvesting sources not only for providing energy and sensing application, but this idea of puff that I showed to you. See this particular slides in the back, actually, right? And this puff has application in several applications. It can be used for key generations. It can be used for identification purposes, because as I told you, each human has a separate DNA. If you have a separate puff in each of these ones, from then you can identify that this is a particular chip, and if somebody tamper that chip or remove that chip, you will be able to identify, because the puff of that chip is going to change, right? So now interesting aspect is, actually, in the interest of time, I won't go into the CMOS based type of things, but in my research lab, we have developed this adiabatic logic based these puffs, actually, which are energy efficient. We have also developed some sort of this magnetic, you can say magnetic tunnel junction based puff. But here what I'm going to show you slightly different. I'm going to show you the energy harvesting and sensor based puff design, actually. So here, if you see, this is my IoT device. My IoT device consists of a power source. This power source could be some sort of a battery, or it could be some sort of you can say energy harvesting type of thing. It could be RF, it could be a solar energy, it could be a other type of energy mechanisms. Then you have this IoT system. You have this transceiver. You have this microcontroller, and then you have the sensors, because these IoT devices are sensing something, right? They are mostly sensing something. So now, one interesting aspect we want to look into: can we use some of this power source or the sensors for security application, right? So we are providing some extra thing to them beyond their work of doing the sensing, right? So here, one such example is, I'm going to show you, is an example of the solar cell. Solar cell is one of the mechanisms by which people can use for energy harvesting applications. So here you have the IoT devices. By providing these solar cells, you can provide some energy to the system. So the battery doesn't have to drain always, because the solar cell can be used for recharging applications. And then we develop this puff from the solar cell. So the interesting idea, we want to use this solar cell both for developing energy, but also can be utilized for the puff application, right? So this is the sole idea. So this is the idea. We looked into how can we develop these puffs from these sensors or these solar cell type of ideas. So as I told you, is that this is because of process variations. You can say when you put the challenge across this thing, it is going to be different. But how this puff is being designed now, so let's look into that. So in this particular case, we looked into solar cells, we looked into thermistor sensors, we look into thermistor sensors, solar cells, we look into also photoresistors also. We looked into 3 or 4 different types of sensors mechanism, and we see can we develop some puff from that one. So in this particular case, let's say you have these solar cells. These are 8 of them, and now this is the microcontroller, and it is being connected to pin number 0 to 7 of that microcontroller. It's an example, illustrative example. And then you have the ADC. the ADC is going to convert this analog signal to a digital signal, and then it goes to a microcontroller. So what we are doing in this particular case, we have our own proprietary algorithm that we developed over a period of time. And from these solar cells, because if you see when a light falls on the solar cells, they are going to produce some output voltage. And what we are proving in this case, that if we, by our algorithms, take care that this from this output voltage that is produced by the solar cell, that is going to process by the ADC, and our algorithms generate a unique 128-bit signature. So in other words, a unique 128-bit signature is being created from this solar cell. So the idea is that, let's say this, if I replace one of this solar cell and I take it out and I replace with a counterfeit one, then the signature that I'm talking about, 128-bit to be created, will be different. So now you can say this is considered more like a VIN number of your car. When you drive, you have the VIN number of your car mentioned into that one. But right now the VIN number of the car is already encrypted, is already written on the device. But what if you don't write it, you create a chip, and the chip is generating the automatic VIN number. And in other words, whenever somebody tried to tamper the device, the VIN number is going to change. So in other words, people can know that if your car has been tampered with. I'm giving just an illustrative example here. So in this particular case, we have the solar cells there, and from this we are able to create a unique signature for this IoT device, actually, right? Now this is good. Now how can we move it further on? So now another interesting thing in this particular case is we looked into, can we use this solar cell or the sensors? One interesting aspect, I want to go back to the previous slide. I want to show you, I showed the example of these solar cells, but the same algorithms we have tested on thermistor sensors and few other different types of sensors. So this algorithm is very generic in nature. It is not only targeted toward the solar cell. Any of this aid, as long as they provide some sort of either they are producing some sort of, you can say, voltage or whatever things, we can easily create a unique signature out of it. That's what we have a patent on this algorithm. So now we move further, and we thought, okay, this is good. Can we do more with that? So if you talk about the security from the primitives, the other important thing that people look into is a true random number generator, right? So if you look into true random number generator, so we have the solar cell, the light falls onto that, and then you can see in this case, the algorithm that I showed to you, the true random number generator should be very random in nature. So how can we create puff out of it? So one interesting aspect is this particular case, and the light is falling down, you look into the systems, or the signature, which are slightly stable in nature. So in this case, you already know that this type of within a one standard deviation, the things are almost constant, but after that it is going to become random. So we pick these things for generating the true random number generator, and we pick these things for generating the puff. So in other words, the stable entropy, we use it for puff, and the more unstable entropy we use for true random number generation. So this is the sole idea. So you have this solar cells, and then you put it, and this is the puff voltage expression. This is the true voltage expression. The static entropy can be used for creating puffs, because you don't want your puff to change every time. Your puff, let's say if I'm driving a car here in Knoxville today, I take the car to, let's say, somewhere in the Brazil, my car should produce the same type of VIN number, right? Otherwise, so in other words, it should be same. So in other words, we need to have a static entropy to be utilized for puff, but for the true random number generator, it should be different every time. So we want to have more dynamic entropy. So that is the whole idea, and we use it for the puff generation. Now let's move and let's talk about, in this case, when we talk about further about this car and automotives, you can say the interesting and the challenging problem with many of these cars is that if you buy a car, you hold that car at least for 20 years, right? Now, interesting thing is that, let's say if I buy a car right now, and who knows, after 10-20 years, maybe some more powerful type of computing systems comes into picture, like quantum and all those things, then what if my system becomes vulnerable? So people are already looking into that. You can say they are trying to replace some of these algorithms by the post-quantum resistant algorithms, and there is already a lot of work going on to that. But the interesting problem is that how can you make them energy efficient and all those things? So that is the work. A lot of people are doing the work in this area. So in the interest of time, I took already a good amount of time, so I will move forward. So here you can say this is one example of the puff in the automotive, the puff we talked about. So here one such example is that when an automated software update is done, so instead of people here, somebody who is a malicious guy can do a lot of things here, and they can install some unauthorized thing into your car. But by using puff, you can just make sure that only the original equipment manufacturer can install the update in your car. So by using puff, you can have more reliable systems actually. This is another example. You can put puff into the electronic control units. So you can see each car has so many electronic control units, almost more than 100 electronic control units. For example, these electronic control units are deployed in the car for measuring the temperature, pressure monitoring. They can be used for, you can say, for your AC systems and all those things. So there are, or it can be used for, you can say, during collision detection system. So you can put some sort of these puffs inside the car, and these puffs can, let's say if somebody tamper with your temperature pressure sensor, then system can know actually, right, that okay, it has been changed, the signature has been changed. So this is some interesting idea. Now I will quickly tell you that one interesting aspect that we also look into the security from the 3D printing perspective, a very interesting work. So here, if you see, there are a lot of 3D printers that are available, and they are all CAN based, right? This CAN based is a control area network bus. The same bus is being deployed in your in your cars. Actually, that's why the car could be easily hacked, because many times this CAN bus are completely unencrypted in nature. So people can snoop the data and get all the information out. This is an example of a 3D printer where this different components of this 3D printer, servo motor, printer head, are all connected to the CAN, and an attacker can get access to the CAN and put a compromise module there. And now in this particular case, you can say the attacker was able to, this is one of our paper, we showed some demonstration that as an attacker, you can change the temperature of the 3D printer as a malicious user, and by so you can do some harm to the device being formed. You can make it vulnerable, you can make it weak, you can make it slightly whatever things you want to do with that, right? Or you can completely halt the production system. So what we did in this particular case is that, you see, because the problem in this case, there is a one CAN bus, it is going to all the places. So we propose a hierarchical model. In this particular case, it is more like, you can say, a tree based structure where the CAN is not like a single CAN bus going to all the places. We make it more like a hierarchical architecture. And by using the hierarchical architecture, the benefit in this case, you can, if there is a one portion of the thing that is being attacked, you can isolate it easily. So in this particular case, we use a mechanism of puff combined with this hierarchical structure to make the 3D printer secure. Okay, and this is some demonstration example. So I will ask Professor Ricardo how many minutes I have actually, and then depending on that, we can talk further.
Well, it's up to you.
Okay, so I will speak for a few minutes more, and then we can take the Q&A actually, right? So I gave you different aspect, but this is very interesting. This research, another thing that I will talk to you that is going on in my lab. So we have this magnetic tunnel junctions, right? MTJs, and these MTJs are being used in several applications, but these MTJs have their own issues. The issue is that they have a very high writing energy, and because of that, if you develop system which always writes, then these systems are going to consume a lot of power. But if you write one time to the magnets, and then you just reading from that, then system will be energy efficient in nature. And that's why people are using these ideas for lot of logic in memory architectures and all those things, right? This magnetic junction. So in my lab, what we did in this case, this is a magnetic junction. It can be in two possible states. One of the states could be the parallel state, in which it is in logic 1 state in this particular case. If it's anti-parallel, then it's logic 0 state. So this is how the magnetic junction works. So interestingly, as I told you, people use this idea for developing this hybrid MTJ CMOS circuit. It is a sense amplifier on the top, then it's a dual rail logic, and this MTJ on the bottom. I will show to you with the circuit actually, maybe this one. This is how the circuit looks like. So you have this sense amplifier. This is your dual rail logic here, A and A bar, and then you have this MTJs here actually, and then it's computing F or F bar function in this case. So what you can see in this case is that the system, if you don't write into the MTJs, mostly if you keep it constant, the system automatically reads in a uniform way. But as soon as you flip the magnet, you see the spike, right? Okay, and if you so so if you want to develop some encryption hardware which is energy efficient in nature, how can I take care of that? So we looked into this problem for some time, and one interesting aspect I want to show to you is this one, which is here. So if you look into this, many of these encryption algorithms, they have a component called S-box. And if you look into the existing literature, people say that in the conventional CMOS design, don't use a lookup table based approach, because the lookup table based approach is going to consume a lot of power. You develop this circuit using combinational circuit, and that's how people develop in CMOS. But if you see in this MTJs, the lookup tables will be very good, because once you write to the MTJs, it can just work as a lookup table. So you're not writing to the MTJs every time, you're just writing one, and then you're just making it work as a lookup table. So what we did in this particular case, we replaced the component of the S box with a complete lookup table based S box of an encryption algorithm. And this is one such example. So you write to the MTJs, and then this is more like a lookup table. It is more like, you can consider like a mux based architecture, right? It's a muxes, and then you're taking the data out. So the benefit in this case, if you see, is as I showed in the previous slide, because the power profile changes as soon as you write to the MTJs. But in our case, we don't write to the MTJs, we just write it one, and then we use the lookup table based approach. So the benefit of that, you see in this case, that the current consumption of our system becomes uniform, because we are not writing to the MTJs every time. Okay, so that's the sole idea. We don't write to the MTJs every time, we write it one, and then we use the lookup table based approach, and then we are developing some encryption circuitry from that one. So because of that, the circuit is secure against the this differential power based analysis attack. And by using this MTJ CMOS idea, we are able to also have the lower energy consumption. So next thing, we also looked into that. Okay, now that's good. Can we use also adiabatic logic with this one? So what we did in this particular case, we changed the sense amplifier on the top. As I showed to you, this is a sense amplifier on the top. This is the VDD. Because this VDD can be replaced by a V clock, like I discussed with you. So in the next task, we make this adiabatic based sense amplifier. So we develop a sense amplifier. In this particular case, it's an adiabatic sense amplifier. So and we discussed in the previous few slides that adiabatic sense amplifier can help you to recover the energy. And this is the clocking is sinusoidal clocking. So now we are using the same idea that we discussed by using magnetic junctions, but by using the idea of adiabatic logic, we are also able to recover the energy back, actually. Okay, and so interestingly, this is the switching problem, but we saved that, as I told you, by using the lookup table based approach. This is the whole encryption one round of presentity that we implemented using this idea. And you can see in this particular case, the energy in the CMOS is 77.3 around, and in this particular case, we are able to have almost, you can say, this is an example of S box, almost like you can say 50% reduction and all those things. And this is some graph. You can say that with frequencies, you can say by using magnetic junctions along with adiabatic, you can do some more energy savings, and it's a pretty number, 6% and all those things number. And then we do, so one interesting aspect I want to tell you, which I did not talk today, is the clock generator. Clock generator is very important component, because that is a component that is going to help you recover the energy. So we did some analysis on that one, how to develop an efficient clock generator. And if you change the capacitor value, inductor value, that's a separate topic actually, which but we did some analysis, and we identify, okay, this particular inductor and capacitor can give you better energy efficiency and all those things. So this is some of the work that is going in my lab. Currently, we are also developing some field programmable gate array FPGAs from this adiabatic logic. We have a couple of papers that are published on these topics recently, and the idea is that if you develop a secure by design of an FPGA, then anything that you map onto the FPGA, let's say the whole idea is like this: if you develop this adiabatic logic FPGA and it is consuming a uniform power consumption, then you map let's say a cryptographic algorithm, or you map an AI algorithm or anything onto that one, it doesn't matter. The system is going to consume uniform power, because the underlying hardware is design such that it consume uniform power. So we are looking into some solutions of secure by design of FPGA. We have published a couple of papers on that one. You are welcome to look into that. So in the interest of time, I will stop here and I will be happy to take any question. Thank you.
Thank you very much. So my looking for questions. I see no questions yet. So if somebody has any question, please can you do it as soon as possible using this chat channel? But I have one about the adiabatic circuits you show.
Uh-huh.
There is any restriction to size of logic in a gate? For
That's
example,
a
if
good.
you use a AOI function with more complex logic, it's also okay or no? What are the
No, that's a good question. So if you see, we mostly in this particular case we have tested like the simple logic gates like XOR or three input XOR or four input XOR, right? Because this is the mostly the circuit that we are using. So you can develop the more complex circuitry, but you have to make sure that that the more logic you're going to put, you have to make sure that what is the frequency of your device. The more, in other words, you can make a big building block that is operating and working as a logic gate, but then probably you may have to do some analysis on the operating frequency of that logic and according along with that energy consumption. So this number is going to change based on the logic that you're implementing.
okay? So I see no more questions here. Okay. So I have to thank you again, Himanshu, for the very nice presentation. It's you you have presented a large set of important topics related to the talk. So thank you very much,
Yeah.
and so I'll see you in person in 9 days. No?
Thank you, and it is very nice of you to to provide me this opportunity to present our research. And thank you, everyone. And I'm also looking forward for your visit.
Thank you. So just a short remark that if you lost the past talks, and also if you wanted to recommend the Himanshu talk that was done today, they are all available in this YouTube channel. Soon we are going to announce the next CASS talks, and also you saw in the talk of Himanshu there is a large set of issues related to IoT, and we should soon announce the first excuse me, Latin conference on IoT.
That's very nice.
The first edition will be end of April next year in the city of Fortaleza in the northeast of Brazil. So it's very easy to reach. There is direct flights from many cities, including Miami, for example. So it's not so far from North America.
Yes.
And this new conference is intended to be the flagship. Will be the flagship conference of IEEE IoT technical community
Mm-hmm.
Latin America. So an international conference in the region that will move between Latin American countries each year. No?
That
So
will be
the
great. That will be great. I think like so it will be something like similar. It was like WFIoT was there. So you this is Latin, something like Latin.
it's similar to the old forum IoT.
Uh-huh, uh-huh.
So the IEEE IoT technical community is sponsored by 12 IEEE societies,
Mm-hmm.
including CASS. And then the old forum on IoT this year will be in Ottawa,
Mm-hmm.
November. And then the technical community decided to start promoting flagship conference also in the different regions of the world. And the Latin one will be the first.
Okay, that'd be great.
So it's going to move, as I told, between countries in Latin America, and the first edition will be in the beautiful city of Fortaleza in the northeast, in the border of the ocean.
Okay, that's
I
great.
hope that all of you will be able to come to the conference next year. So next year there is several opportunities to come to South America.
Yeah, I looks like.
One is Ascas, that will be so in the wine region that I told you in the beginning, and the end of February, the end of April in Fortaleza, the Latin Conference on IoT. Then end of August in Manaus, the gateway to the jungle, the SBCCI, Chip in the Jungle. And then in October, we are going to have the IEEE IFIP Versailles SOC conference in south of Chile,
Mhm.
in Puerto Varas, Chile, beginning of October. So it's a good year to come to South America.
Yeah, it looks like a lot of exciting events. Yeah.
Yeah. So thank you all. Thank you again, Himanshu. And
Thank you.
so soon we are going to announce the next CASS talk. Next week we are not going to have CASS talk because it's on the way to VLSI, IS VLSI in Knoxville.
Thank you.
So bye bye.
Bye.